He is Semiconductor IP and Associate Architect, Certified Independent Director, and Deep Tech Startup Advisor. Over the years, he has led advanced processor and SoC architecture programs across global organizations, including Qualcomm and Intel, contributing to high performance compute platforms and innovations at scale. Beyond his technical excellence, he actively mentors startups and contribute to governance and responsible innovation initiatives. We are truly proud to see VITians achieving such global impact. Please join me in warmly welcoming our esteemed alumnus, Mr. Deepak Tanna. And this session is alumni guidance session, specifically for core and IT people. And these sessions are organized by in collaboration with Univariety. So about Univariety, Univariety partnered with Vishwakarma Institute of Technology, offers a comprehensive alumni management platform headquartered in Hyderabad with a pan-India presence. Univarity's technology-driven approach leverages alumni to provide top-notch guidance to students. So we'll start with the session. So I request everyone to listen to alumni, connect with the alumni, discuss your ideas, discuss your innovation with alumni. Thank you. Over to you, sir.
Thank you, Dr. Pankaj, for the generous introduction. I don't see students actually.
Sir, can you on the camera of the students? We are unable to see them.
Yeah, just a second. Disconnected from.
I think that laptop has got disconnected, sir. We are unable to see the students. Like
Yes. I got this.
yeah.
Are you able to hear me, Shravya?
Yeah, we are able to hear.
And the room people are able to hear me?
I think they are joining in again.
Yes, audible. You are audible.
Okay, so I think, let's get started while you fix the camera, right? No matter, doesn't matter. So, good afternoon, everyone. Thanks to Univariety and the Institute, Dr. Pankaj, for inviting me here, talking to students. 30 years back, I was sitting on the other side of this room. It seems this conference room or this auditorium is built newly, looks like, but I never imagined that, someday I'll be on the other side and, talking and addressing to the students, right? So, good to be here. Thanks for the invitation. So, before I start this talk, right, I want to just, by a show of hands, ask you people, how many of you feel uncertain about, how AI will impact your career? Just by, show of hands. I don't see the hands actually. Can somebody, Shravya or Dr. Pankaj tell me, how many, like, is it less than 50%, more than 50%? Nobody is raising hand. Everybody is certain about the future.
No, you can see the students.
Yeah, I see the students, but I don't see the image is too small, right? So can you help me with, to just understand how many of them feel uncertain?
Maybe you could just help with the approximate number how many students have
It's
raised.
just less than 50%, more than 50%. Nobody, everybody feels certain.
Nobody.
Oh, everybody's certain about the future. How AI impacts their career. That's good to know. That's very confident crowd I'm addressing, and I would want to if I was in the hall, I would want to know how many of you have clarity on where do you fit in this changing, fast changing tech world, right? But again, as I don't see the hands here, I'll just move on and talk about what I'm going to talk about today, right? So in this AI world, what I want to show, what is most important today is how AI is not replacing engineers, but it's creating huge amount of opportunity for this semiconductor cycle in the human history, basically, right? So I'll talk about initially what is changing and what is shaping the semiconductor industry, where the innovation is happening in the semiconductor industry, the semiconductor ecosystem. And the third topic I will talk about is showing you where you can position yourself, what are the opportunities, roles, skills that you can look forward to in this industry, right? So before we look at the current trends, we need to look back in history, what happened in the past, and how we got here, right? So before 2000 and during the PC and the networking era, the Dennard scaling enabled frequency scaling. The transistors got smaller, more number of transistors got on the chip, generation after generation. Frequency was scaling nicely, and sometime in during 2000 to 2005, they're not scaling, stopped giving results, right? So then industry pivoted to multi-core, multi-socket architectures, right? So that was the PC networking era. Then it was the mobile era where billions of mobile phones got sold, and then it had its own cycle of CPU evolution for extreme low power devices, right? And post mobile era, now we are at the beginning of AI era, right? So and this AI era is driven by availability of huge amount of data that we need to process, right? And data is the new oil, and to process this huge amount of data we need better, faster, cheaper chips, right? So and the other thing that is driving this semiconductor cycle is the e-vehicles, the automotive innovations, the need for always connected devices, right? And if you see the TAM is the total availability of market, right? Semiconductor, all semiconductor vendors across the world, how many chips they have sold in terms of dollars value of sold products, right? So that has been increasing consistently until last few years. We all were hearing that by 2030 it's going to be $1 trillion market, but in last couple of months McKinsey analysts have revised this forecast, saying that now it won't be 1 trillion, it will be 1.3 trillion. And then some analysts, in fact, they are more optimistic, they say it may grow to 1.6 trillion or so market, right? So that's showing a significant growth opportunity in the semiconductor in the next few years or the decade. And the transistors on the chip have been scaling from, say, millions of transistors to billions of transistors on the die or on the package, right? And then with the mobile era, we saw that hundreds of IPs, the intellectual property, right? The module that gets reused across different products, right? That we call is IP modules, right? So the hundreds of IPs got integrated on the system on chip, the SoC or the package, right? And this datafication, this EV revolution is, creating humongous complexity. The complexity that we are going to see is going to be around 100x than what we are used to handling this kind of complexity. And all this while from scaling the transistors from tens of millions to billions of transistors, the EDA is at the foundation of enabling this level of integration or design productivity for the design engineers, right? EDA tools have enabled this handling of this complexity, and now we need AI or ML based tools to accelerate handling this kind of complexity. And this era also, because of this complexity and the AI demands in different industries or different domains, is demanding to build specialized hardwares. Now if I zoom into India specific opportunities, India today has around 20% of global talent already doing design verification, physical design, architecture, all this very talent demanding work for the past 2 decades or so in India. And if you see the market for the India, it is today $45 billion of semiconductors imported, and it's expected to grow and then cross $100 billion. And if this makes me recollect, few years back, China's semiconductor import bill surpassed their oil import bill, right? So if we see that if most of these IC vehicles switch to EV vehicles, we may surpass this $115 billion of importing semiconductor chips if right actions are not taken today. And that's why you see a lot of announcements from government supporting manufacturing in India, and this additional incentives, design linked incentives for developing cutting edge chips in India, right? So we have today a significant presence of semiconductor design centers and services companies and education companies, right? And if you see in the last couple of years, I have seen like 40 plus kind of startups have come up in semiconductor space. I had never seen this kind of a number semiconductor development startups, right? And which have raised significant amount. And that's the trend globally as well. So this graph is showing a little bit old data 2023, but I didn't have time enough to get this recent graph. But in 2025, there is estimates that there are close to 200 unique startups operating in semiconductor space, right? And they have received significant funding. So the capital is moving towards more investment in semiconductor development. So with that, let's look at the semiconductor ecosystem, right? Where the innovation is happening. So this top layer here is, showing the compute engines, right? We all are aware of CPUs, right? For the servers, client, mobile. At least, when I was in college studying at VIT, those days we knew only about CPUs. From the 1996 to now, if I see, we have lot more kind of compute engines being developed and getting used in wide variety of devices and systems, right? So CPUs in servers, they have a different demand. They require very high performance, right? The mobile requires extreme low power. So that leads to a different kinds of architectures for the compute engines themselves, right? And the performance per watt is the real currency, whether it's mobile or it's a server, right? Even for the server it matters, because the power is one of the critical factor in data center, where you have thousands of chips running in the data center. And even if you reduce 1 watt of power for one chip, so that boils down to huge amount of electricity saving, and also reduction in the cooling requirement for the chips, right? And we moved from just CPU development to multiple kinds of cores on the same SoC, right? We call it as heterogeneous systems, right? So the workload demanded that because of this power constraints, and depending on the workload, if workload demands high performance, then you run the cores which are optimized to give higher performance. And when the workload demand is different, it doesn't require ask for a high performance, you can run power efficient cores, right? So we call that as a big little or perf power cores, right? That's the heterogeneous systems. And then on top of that, in the same system, we added graphics processing units to handle the graphics workload. And then GPU, it seems now getting used and very popular and efficient for data center training as well. Now with the different kinds of workloads, there are a lot of domain specific accelerators that are coming up. Why? Because it's all driven by power, performance, and area constraints that we all face in the architecture and the design domain, right? So there could be the accelerators which are like TPUs. You might have heard about the tensor processing units, right? That accelerates certain kind of workload. Or that could be the NPUs or the VPUs, the visual processing unit or the neural processing unit, that processes significant number of images or the video per second, doing the image object detection or object tracking in the video, right? Real time or in the offload offline traffic, right? Stored in the storage, right? So there are different types of domain specific accelerators that are getting built. So earlier, we had we called it as ASIC, application specific integrated circuits. They had, during the networking era, they were like, network processing, packet processing engines or the network search engines, right? But now this accelerators that we are talking about, they're accelerating, certain kind of data flow graphs, or certain specific machine learning or deep learning algorithm that is built for the specific domain. Every domain has a special different characteristics of the workload that runs on. And then the general purpose computing, whether it's the GPU or the CPU, they are general purpose. They are built for general purpose, right? Not for the specific purpose. So domain specific accelerators help achieve more efficient performance compared to GPUs and the CPUs. And that's why there is a tremendous effort going in developing those. There is a huge amount of capital flowing in to develop those accelerators. Apart from that, if you see, recently there is a open source RISC-V instruction set architecture has come up, right? And then industry is still it's not at that maturity level, and the software stack availability is still not there. But this RISC-V kind of course could be more attractive for the energy efficient or extreme low power edge devices. MCUs are getting, the microcontroller units are getting used in embedded applications, right, in your appliances or other embedded devices, right? Now the domain specific accelerator we talked about, it addresses specific optimized algorithm to be processed efficiently. Now what if you have got some MLDL AI algorithm that you have accelerated using your custom silicon. Now tomorrow you find efficient algorithm to implement for your specific business case, right? Then you have to build another ASIC, the specific accelerator. So that requires another huge investment. So now people are thinking about why can't I come out with reconfigurable computing, right? Where I can tomorrow if my algorithm changes, then I can run that domain specific workload on the reconfigurable compute, right? So it's somewhere between ASIC. You can see view it as between somewhere between ASIC and the FPGAs, right? So that I know there is one startup in India that is doing very good work on this reconfigurable computing. And some more things are under development which I have not listed are, for example, the neuromorphic computing or the memory stir based analog inference dies, right? So we haven't seen those still commercially available. They are still under development, and people have been researching their workload, how it performs on those kind of accelerators, right? But those are some of the other areas that are emerging and people are working on. So moving to the multi-core architectures that we built for client and the servers, right? So they led to development of coherent fabrics, right? So that leads me to the next important topic here, the middle layer, which is where the real bottlenecks today exist, right? So the coherent fabric that we talked about, what is coherent is when you have multiple cores running multiple applications or one application running on the different cores, and if one application modifies the data, then all the other cores should see the data consistently, right? What was last modified, that's ensured or enforced in hardware using the coherent interconnects, right? So this on-chip fabric is extremely critical because the workload demanded bandwidth and the latencies get impacted with the way you build your on-chip interconnect fabric, or if it is a scale-out system where you connect hundreds or thousands of such chiplets or SoCs to build data center class systems, right? So then the inter-chip communication or the fabric bandwidth and latencies matter. So currently the compute has scaled very well in the past. Now the bottlenecks are in the the memory bandwidth and the interconnect bandwidth, right? So moving data is more expensive than doing the math in the AI kind of workload where you have to do matrix multiplication kind of basic math, right? So calculating your activation functions based on weights and the input feature map and so on, right? So the interconnect fabrics also have evolved significantly because on if I talk about on the chip interconnects, there are different kind of interface protocols people use, right? So the, as I said, the core connecting multiple coherent cores, we need coherent fabric, and then there are non-coherent engines basically which require movement of data that is not coherent, right? So basically the IO your IO, which is in the ordered domain, but it's non-coherent, that merges with the coherent traffic, right? So that's critical. Then how do you implement your cache hierarchies, right? So within the uh, within the chiplet or the SoC, how do you connect your L2 and the last level caches, how much bandwidth you can achieve through this cache hierarchy, how much snoop traffic you can achieve, what is the topology, how you connect, tens of or hundreds of cores efficiently on the interconnect so that you achieve your bandwidth and latency targets, but you don't exceed your power goals, right? How do you ensure that certain real-time sensitive traffic don't suffer higher latency because there is some high bandwidth hogging core is fetching a lot of data from memory, so that requires you to think about upfront quality of service you can ensure on your interconnects, right? Then the other major bottlenecks today in the AI systems accelerators people are facing is the memory bandwidth and the memory capacity, right? So that's another critical. If you have 30 or 40 64 cores on the die, and then all of them wants to get data from memory, then that puts a huge demand on the memory bandwidth. And then there are new technologies coming up in the memory design itself, where you have memory on the die, and then you have memory on the package, you have off package memories, the storage, the when you have hundreds of terabytes of capacity required for your big workload, then you connect those storage solutions using the CXL interface, right? Compute Express Link, that's a new specification, interface specification to connect your IOs or the memory storage external to your compute systems, right? Then industry is now pivoting to chiplets. Why? Because with the advanced tech nodes, achieving high yield with very large dies is getting challenging. And also there are certain functions, certain IPs on the current SoCs which doesn't need to be on the advanced node, which are very expensive to build, right? They can run on, say, old your previous generation nodes like 28 nanometer or 45 nanometer kind of a tech node, right? So this chiplet technology enables you to have chiplets, the compute engines built with latest technology node and some IO chiplets built using the old technology nodes, right? This is enabled by the advanced packaging techniques and the industry standard UCI interface, right? So you may want to learn about this universal chiplet interconnect express, right? So this specification which enables interconnecting chiplets from different vendors from different technology nodes, right? The power management is the extremely critical function. Every engineer working on semiconductor needs to be on top of, right? Be it a mobile segment, be it a client segment, be it a server, be it accelerators, no matter what, right? So you have say you have hundreds of IPs on the chip, right? And then you have a power targets for your chip, right? And as we discussed, we discussed in the previous slide the big little course and power and performance course. So similar to the outside of the CPU, the non CPU IP course. For example, you on your laptop you have a USB controller, and then while you're doing browsing or running your some simulations on laptop, you may not need the USB drive. So your USB controller can go to sleep state. So you power gate those, and as you power gate them, that makes more power available for your compute engine to run faster. So there is a dynamic voltage and frequency scaling that could be applied to CPU cores and to different IP cores as well, right? So that uh, adds another complexity on the chips, right? Because now you have to deal with multiple voltage domains, multiple power domains, multiple clock frequencies that you need to close the timing on, right? And the EDA tools have been evolving, and they have started adopting now machine learning assisted design, right? Because as we said, the complexity is going to 100x, and we need now the better efficient tools to handle those complexity, right? So some of that we'll talk about on the next slide. How as an engineer, apart from the EDA, how you can make use of the AI things, right? And there are photonics interconnects, since copper is reaching its limit, and the the demand for the interchip communication is exploding, right? You want to move huge amount of data across chips, right? So now there are optical interconnects also under development. So with that, now let's look at So basically in this bottom line is that the data, in addition to your high performance compute, the data movement is critical, and the data movement with efficient power, right? You don't want to be consuming hundreds of watts just to move your data from memory to the compute engine. So that's why the data movement through the interconnect is critical, and that's going to be the future differentiator. So let's look at uh, some of the roles that you could take up. So each of these roles here shown, it's a full career path in itself, right? So starting with the architecture and design, uh, you can define the specification of the SoC. What are the requirements that the end workload use case requires, right? What all IPs I would want to have on the chip. How do I interconnect them? What bandwidth the interconnect need to have on the chip. All those specifications we need to create. What configurability I need to have. Now when I'm building the IP that I want to capitalize on the investment done in building certain IP, for example, USB controller or interrupt controller, PCIe controller, right? I want to reuse them across different products as well as different market segments, right? So I need to build those IP upfront configurable, design time configurable, and as well as software configurable when it is running in the system to create different product SKUs, right? So once we define the architecture spec, then the architecture spec needs to be translated to the microarchitecture and the RTL design. Then you need to do upfront invest in doing the performance modeling of the architecture and the microarchitecture that you have created, so that it meets your performance goals within the power budget that you have for the specific product, right? The verification validation, another critical function. You need to do the functional verification whether the design intent, as listed in the specification, it meets in all conditions, right? So you do the performance and the functional verification. You need to do now, as the accelerators are very tightly coupled with software in some cases, right? The specific workload optimizations you are doing in the accelerators, then you want to do the hardware software co-validation. You want to do emulate the design on FPGA emulators to make sure that nothing is broken before you actually manufacture the die. Then there are a complex IP SoC debug infrastructure you have to put in the die, because once your silicon comes back and certain use cases or application breaks, or the test fails, then how do you quickly get to the root of the problem, where on the die with hundreds of IPs interconnected, which IP is causing the issue, right? So you have to do upfront pre-silicon thinking, and a huge amount of investment is done in planning for the SoC or the IP debug, and a lot of hooks are put in before silicon goes for manufacturing. The physical design and silicon realization, this is another challenging area where you want to convert your RTL code to your gate level netlist, and then actually place and route and do the timing closure, right? So in the previous slide we talked about power management. You have multiple voltage and power domains, right? So that's where now challenges comes, right? So you have to make sure that your IPs and the SoC can tolerate different voltage variations, and and then you design your power delivery network such that your timing doesn't impacted with different variations in different voltage domains, right? Post silicon and debug engineering is another critical area, where once the silicon comes up, it's one has to be uh, ready with the boot up, silicon boot up, and application software running pre-scripted planning, right? Because once the silicon comes back, the race starts, right? Because now you have to qualify the product and release the product in the market, right? So that's very demanding job, where how efficiently you can bring up your silicon. Once the silicon comes from fab, if it can boot up your operating system on day one, and then you start running your applications, and do the triaging if there are any failures, and then analyze and get to the root of the problem very quickly, right? DFT test engineering, again, you identify what all test patterns you need to generate, so that on tester, without taking a lot of tester time, you generate the right patterns to test each and every gate and flop if it's manufactured as expected, right? Now if you see the RTL, how AI, you can make use of AI, right? It enables RTL engineer to say, if you are starting some IP from scratch, then maybe you can make use of your corporate enabled tools to generate the initial code. Still we have repeatability issues from this Gen AI. We cannot rely completely on the RTL code that is generated by AI. We still need the engineer to do the thinking, but no, it can help accelerate the RTL code development when you're say building from ground up, or if you have your existing design and there is a handoff from one engineer to another engineer. So understanding the RTL code, it can help in understanding the RTL and commenting that some sections which are difficult to understand, make sense of that, identify the corner cases or the bugs in the RTL or the compile issues and get to the root of the problem very quickly. That's how it can enable you to improve your productivity at the RTL level. The verification, again, same thing. When you're running hundreds or thousands of test cases, right? So and many of this regression tests fails, right? How do you now get to the root of the problem fast? How do you triage the test failing because of the same root cause? So that's where again AI can drastically improve your productivity in this case. Similarly, post silicon validation as well. Now, place and route and synthesis, again, ML algorithms could be used to do efficient implementation of your logic in actual at circuit level, and make sure that your timing and power goals are met, right? So really none of these jobs are going away, but you have AI available to accelerate your productivity, right? So you can, if I were to use the analogy, if I had the bicycle to go from one place to other place, now I have got power of the speed of the Ferrari car, right? But then I need to know how do I drive that car safely, right? So that's critical. So this all of these roles are still very much required in the next decade, right? So it's not going away anyway, but it increases. We need many more engineers to handle this complexity, right? So when we started this presentation, I asked you one question, how many of you feel uncertain now after going through this opportunities in semiconductors and the innovation in which all areas the innovation is happening, and all this roles requirement. I hope it even if you had some uncertainty in your mind, it helps reduce the uncertainty, right? Now no, you need to the call to action is you need to ask yourself, in this ecosystem, the domains that we looked at, the CPUs, GPUs, accelerators, interconnects, power management, in which domain you want to position yourself. The second call to action is in which of these skills you want to focus in developing these skills in your next year or couple of years, right? That's what will help you plan your career in the semiconductor, right? So don't just look for the job, look for how you can architect the future. So with that, I can explore questions together if you have any. Thank you.
Students, if you have any questions, you can just move forward and ask your questions.
Students, if you have any questions, you can come here.
So, I was told that I have 40 minutes to talk, right? So I had removed my, personal career journey, 26 years of career journey in semiconductor, and my leadership nuggets out of that. So I had removed those slides. If there are no questions and if there is interest, we could, go over some of that in next 5-10 minutes, if
You
there
can
is
take
interest.
5 more minutes. Yeah.
Yeah. So, okay. So, when I started with Intel, as I started my career with Intel on server CPUs, right? With QPI technology under development at that point of time. The CPUs were switching from bus-based interconnect to point-to-point interconnect between multiple sockets, right, to scale the systems, right? And it was a new team, and there were server market challenges, and QPI interface was first time, right? That was a significant ramp up required on understanding the QPI interface, understanding the new microarchitecture, interrupt architecture. Those were the challenges that very first time when I was working on the Intel CPU development I had to face, right? Then in after 2003, in 2007 is when we got our first success with the CPU developed out of Bangalore team, right? And we all got this nice T-shirt that we still keep it because it has very nice message on that, right? So we had again steep ramp up, new features, totally different architecture. It was a short runway, but then the mentors that you have in your team, right, that helps you to navigate some of the challenges, right? And then the journey continued with more and more number of cores, right, handling power management, the deadlock issues, and power management, and then uh, moving to a different area completely, right? The building the PCI root complex, handling the coherent traffic, and uh, then for some time I had a curiosity about what is different between the mobile platforms and the server platform. So I pivoted to Qualcomm, where I led development of big little ARM-based CPU subsystem, and delivered 4 generations of Snapdragon processor during that time. Then I returned back to Intel because again, I felt uncomfortable with my comfort. So once you learn in depth and you're on top of the things, and I actually I look for to expand my skills and the knowledge horizontal, right? So again, I decided to come back to Intel, and during my second innings, I started owning multiple SoCs and the multiple fabrics architecture that continued for industrial IoT and different use cases. And then, building the ground up new NOC for the edge inference SoC that provided tremendous learning, identifying a lot of architecture features, right? Then I got some opportunity to do the SoC performance analysis. And then, now I'm owning the protocol bridge feature roadmap for the multiple IPs that goes in the different market segments, right? So why I'm sharing this is to discuss some of the leadership nuggets that helped me grow my career in this space, right? So when we pass out of college, we have strengths, right? We carry some knowledge and some skills, right? So we apply those to deliver what is expected from us. We build the performance currency. This performance currency helps you build the trust and the relationship currency, right? People start trusting your abilities and the things you deliver, right? You build relationship based on this trust now, and this relationship currency helps you with getting more challenging opportunities. And this is a vicious cycle, right? More opportunities you get opportunity to apply your strengths and what you have learned in your job, perform better, build more trust, and that's the cycle, right? Now what I found is that there is very very nice ikigai concept, if you have heard about it. Now, what you love to do and what you are good at, that is in your control. What the company needs or what the market needs, and what the company pays you or the market pays you, it's not in your control. What we can focus on is expanding these circles of what I love to do and what I'm good at. If that intersects with what the company needs and what the company is willing to pay, that helps expand your career best. That's a key thing. And the perseverance pays. As you grow in your career, your the ambiguity that you have to deal with in defining products, designing products increases, keeps increasing, right? So it's bigger scope and bigger impact. So you have to have perseverance, right? And in the process, when you are when you have built competency in one area, and you move to the adjacent area, as you saw in my career path, where I had to once I achieved competency in one area, I had to expand, pick up new areas. So that ramp up is very fast and quick, right? So don't get stressed with that. When we if you look at the stress, the reverse, if you read it, at the end of the stress it will be deserts, right? So it will pay, basically, the whatever effort and little bit of stress you take in, right? So little bit of stress is always good. It helps you grow and expand your capabilities, right? And there is nothing called failure, right? So it's always, even if something gets broken, you get in new bugs or something, don't look at it as a failure, right? So the author Zig Ziglar says, you redefine some of the words in your mind, right? So fail is like first attempt in learning. Learn from the unexpected results you get, and then refine your efforts, and get different results by applying different actions, right? And don't fear if you have to deal with a new area in your job you have never worked on before, right? So face everything and rise, choose that. So and if you have very big complex tasks given, so then it helps to break down that into multiple smart goals, right? So define those complex tasks into smaller tasks where you can measure the progress of those goals, right? They are specific, measurable, and within time bound you can achieve those goals, right? And as I said, career is a spiral journey, right? So when we start, we need to develop the depth in one area, right? So once you have developed the depth in one area, you have become efficient. So you pick up the adjacent area, then you have the T kind of competency, right? You have some breadth and you have depth in one area, and then as you get more experienced and efficient in things, keep expanding, into the adjacent areas to increase your breadth and depth in multiple areas. That helps in taking up the architecture role in the longer run, right? We talked about dealing with more ambiguity and higher complexity as you grow in your career, right? So that's given in this career path, right? So yeah, I think that's it I had. Yeah.
Swati Patel, I think you had a question. Can you please come up to the screen and ask your question?
Hello, am I audible?
Yes, you are a little feeble, but can you be a little louder?
Yeah, now it's audible.
Yes.
Yeah. Deepak, I am the faculty from IT. Actually, the targeted audience are the second year students.
Okay.
So I would like to throw the light on like what sort of project on first year already they have performed a few projects on Arduino. So to make the career in the semiconductor, what sort of small projects they can do in the second year in different domain? Can you throw the light on this?
Sure. Yeah, let me pull up the skills slide that will help look at. Yeah, so what is critical to start the career in semiconductor is RTL and the verification, right? So that's the front end, we call it as a front end, and physical design is back end where you do the synthesis. So you pick up small logic design projects, right? In digital design you have learned the basics of digital design. Then you pick up some small say you want to implement a, risk processor, right? With say set of only 8 to 10 instructions. How would you implement them, right? So you look at what is required for that instruction. You fetch the instruction from the memory, you decode the instruction, you execute the instruction, right? So you do the basic math. The instruction says that add two numbers, subtract two numbers, and so on, right? So you define small simple CPU core, you design it, implemented it using RTL, right? So RTL could be coded in VHDL or Verilog or system Verilog, right? So you need to learn those VHDL Verilog compilation tools. Then you have to simulate that design, right? So you write your own small test bench based on the interfaces that you have picked up for the core that you are building, right? You verify that whether those 8 or 10 small set of instructions that you have defined to be implemented in your core is performing as per your expectation. Functionally it is working, right? So when you simulate that, view the waveforms, it gives you confidence, what you intended, how you implemented using the microarchitecture that you came out with, right? If this core implementation, CPU, small simple CPU core implementation looks difficult, you start with simple counters, implement those simple counters in Verilog, VHDL, or system Verilog, simulate them, and then see how it functions, right? And then if you have access to the synthesis tools, right, then you try synthesizing this Verilog code and then see how the netlist looks like, right? Try to do the timing analysis on this implemented netlist and see what frequency this core can run at, right? What you can now, once you see that this timing analysis shows that you can run this core at say 200 500 megahertz. Then if I want to increase the clock frequency, what design change I would do in this small core that I have designed, right? Does that help answer the question, Swatiji?
Yes, yes, surely the students will follow the instruction and they will do. Yeah, thank you.
So if you can't think of what to design in RTL and simulate on your own, so maybe you can look at publicly available in GitHub or somewhere, the problem small logic areas, right, with the specification, and try to implement those specifications in RTL and then simulate, right? So that helps that build this RTL and verification skills. It will be good learning opportunity. Yeah.
Also, please suggest some links if you are having to prepare for the graduate students like Udemy courses or some NPTEL courses so that it will help them to get the practical knowledge.
Right. So, I don't have those handy right now, but after the this meet, I'll try to find out the best resources and share with the point of contact I have in touch with from Uni Variety.
Sure, sir. We will share with the institute. Any more questions, students?
I guess no question.
Actually, Deepak, I am asking the question only. Actually, it is expected from the student, but sorry. Any internships or some sort of things are there in the Intel that the students will get the opportunity?
Uh, you know, we have central university engagement team who define the internship requirements, who work with the business groups and identify the internship requirements, right? So I would suggest you to get in touch in case if you are your placement cell is not having contact. You could send me introductory email, and then I can find the right contact and forward the your request to right people. Yeah.
Yeah, surely we will connect with you through the manager, and if any opportunity for the good students, we will be move ahead. Thank you.
Sure. Yeah. So even if you don't find a good internship opportunity, today we have so many resources available, right, to identify small problem statements as we discussed, right? You took it, you take initiative, and then build those projects. Basically, it will help you in future finding the right opportunities, right? So when you demonstrate that you have implemented this ABC projects, what you have learned, the RTL synthesis skills you have learned, the microarchitecture skills you have learned, certain domain knowledge you have learned about like caches, cache hierarchy, the interface protocol, industry standard interface protocol, right? When you put it on resume, that will help you find the right opportunity for sure. Even if you have not done formal internship somewhere in the company, but you have taken initiative and you have demonstrated your skills through some project initiative you have taken, right? That will definitely help.
Thank you so much. Thank you. So I guess no questions from students. Thank you, Mr. Deepak Tanna, sir, for your valuable time and guidance to the students on industry in the semiconductor. I invite you on the campus to meet our alumni and outreach department. And thank you, University, for organizing this guidance session for our students. Thank you so much.
Thank you. It's my pleasure talking to you all. All the best.
Thank you. Thank you.
Thank you.
Yeah, thank you. Very good session, and this will help to our all the students. Thank you.
I'm glad that you found it useful. Thank you.
Thank you everyone for joining in. Thank you, Pan, coordinating so well to ensure the
Thank
session.
you.